Hi, this is Larry. I have a interesting and kind of difficult navigational problem that actually brings out a few interesting points about different parts of trigonometry. The first is that you are driving on a course of 105 degrees. What that kind of course of a certain number of degrees refers to as the number of degrees rotated clockwise from due north. So you see on the diagram here, I have due north in purple pointing straight up, more or less. And then 105 degrees rotated clockwise from that brings us to the purple line, which is the course that this car is driving on. And its current location is point A. And then due east of that is point C, which is the center of that circle, that 25-mile circle. That is the range of the signal from the radio station at the center. And so the car going along its path, this purple path, will cross the circle into the radio signal at point B, drive through the circle all the way to, let me see if I can label this point D. Point D down here is where it will in fact cross out of the circle. So we'll look at the two different parts of the problem. I've enlarged this triangle ACB, ABC, not to scale. It's a little bit different of a shape, so I want to bring out the features a little more. Over on the right of the circle, we have the distance from A to C is in fact 30 miles. The radio station is 30 miles away from the current location A. So the top side of that is 30. And BC is in fact the radius of the signal, 25-mile radius. So right at point B, we're in range of the signal, so we are 25 miles away from C. So BC is 25. And that angle, CAB, is 15 degrees. That is 105 degrees from due north is 15 degrees south of due east. 90 plus 15 is 105. So that triangle, we could actually solve right away for AB using the law of cosines. We have two side lengths. We want the third side length, and we have one of the angle measures. But I'm not going to do that. I'm going to solve for the angle theta because we'll see in the second part of the problem we could use to know that angle theta. So we're going to use the law of sines. We're going to say, right up here, sine of 15 degrees over 25 equals sine of theta over 30. And then when you crunch all the numbers there, we get sine of theta equals 0.311. Now I wrote it this way because I don't want to jump to inverse sine right away, because there are in fact two angles theta that have a sine of 0.311. Your calculator will always tell you the first quadrant angle, which is 18.1 degrees. That's not the angle we're looking for. We're looking for the obtuse angle, the second quadrant angle, which is in fact 180 minus 18.1. That angle theta is 161.9 degrees. So now we can actually solve for the third angle up at C, because the three angles have to add up to 180. So we have all three angles now. We can easily solve for that side AB, and I leave that to you to use the law of sines to solve for the side AB. We're going to jump on to the second part of the question. We are now looking at that car driving along that purple path into a signal at B and out of the signal at D. I've drawn in the radius from C to D, and we also already have the radius from C to B. Those two, of course, are the same length. So that triangle there, two sides are green and one side is purple, is an isosceles triangle. And this angle CBD is in fact supplementary to 161.9, and we're back to that first quadrant angle that we found at first. We didn't need it in part A, but we do need it in part B. This is 18.1 degrees. This over here is also 18.1 degrees because it's an isosceles triangle. I'm going to drop a line down, a radius down from the center is going to meet our car path at a right angle. And this is a geometric property that if you drop a radius through a chord, BD is a chord, and if it meets that chord at a right angle, it in fact bisects the chord. And conversely, if you drop the radius down from C and it bisects the chord, it in fact meets at a right angle. So we have a right triangle. We know that the hypotenuse is 25. The angle is 18.1 degrees. And we're going to look for this length, I'll call it y. And we know we can write that the cosine of 18.1 degrees equals y over 25. And we can solve for y that way. And over here, it also equals y. These two triangles here are congruent, the left-hand side and the right-hand side. A number of different ways you can show that. All three sides are equal. And we have right triangles where anyhow, there's a lot of different ways you could prove those two are congruent. So y is the side on the left. It's also equal to the side on the right. And 2y is the answer to the second part of the question. How long do they drive before they cross out of the signal again? So there you go. I hope this drawing and this explanation helps. I'm going to follow this question, so you can leave me a question or a comment, and I'm sure I will see it. And thanks. Bye-bye.